Hello. It's so great to be here. It's a huge honour to talk at the Royal Institution, which I've long been a fan of, and I'm so glad that you could join me this evening. I'm the author of The Star Builders, and tonight I'm going to take you with me on a journey of discovery, the same journey of discovery that I went on while I was writing the book. Now, The Star Builders is about the quest to do no less than recreate the energy source of the sun. That energy source is a reaction called nuclear fusion. And if it can be recreated on Earth, it has the potential to provide humanity with a new, clean source of energy that could last for millions of years. So this evening, I'm going to relay the tales of the people, the machines, and the motivations behind an amazing attempt to, in effect, build a star on Earth. Now, recreating the power source of the stars on Earth might seem like a fairly unhinged thing to do. Stars have temperatures of millions of degrees and pressures hundreds of billions of times those found on Earth. To control the stuff of stars requires the construction of contraptions that test our inventiveness to the breaking point. But despite all that, since the 1940s, people have been trying to do it. Scientists, engineers, governments, and more recently, entrepreneurs too. Controlling the power source of the stars is perhaps the greatest technological challenge humanity has ever attempted, but they are taking it on, and with verve too. They are the Star Builders. Now, I'm particularly excited to be telling you about this today because, having quested for so many decades, a number of big fusion breakthroughs have happened as recently as in the last couple of months. We are in many ways living in the most thrilling time for fusion in decades, and perhaps ever. So this evening, it is going to be a journey of discovery, and it's going to take us to some fairly exotic locations. We're going to go to space, one of the coldest places in the universe, but also we're going to go to the hottest place in the solar system, and we'll even visit the start of time as well. But our journey is going to start in what is perhaps a less exciting location. So this is downtown Livermore, California, USA. A small city on the opposite side of the San Francisco Bay to San Francisco. And I want to start here because this town hosts a very special experiment. I would say that it's the most exciting experiment anywhere in the world today. That's what I think anyway. So let's move from Livermore the place to Lawrence Livermore National Laboratory, where this experiment is based. So this is the National Ignition Facility based at Lawrence Livermore National Laboratory. Now, I haven't put a scale on here, but it's the length of 3 football pitches, American football pitches, of course. And what you are looking at here is the world's most energetic laser system. You can get a sense of the scale because I've labeled some people in one of the pictures there in one of the 2 main laser bays. Now, this laser system is used for lots of experiments, not just those on nuclear fusion for energy. Actually, a lot of the experiments are about maintaining the USA's nuclear arsenal. And some of the other ones are about how materials can survive extreme radiation. So about 100 of the 400 or so shots, as scientists call them, a year, that's a single firing of the laser, are dedicated to research on fusion. And I want to start our journey this evening by relaying to you what happens when this amazing laser fires. So it all begins with a single nanojoule of infrared laser light. Now, infrared laser light is on the red end of the spectrum, but you can't actually see it with the naked eye. But what I've got here is a tiny laser that's in the red color for comparison. And now, look, it's never safe to point a laser at anyone, but fortunately, you're all quite far away from me. And tonight, special treat for being virtual, I can point this laser at you so you can get an idea of it. So this is a red one that you can see. And the amazing things about lasers is that they can take energy and focus it in a very small space. And if you just do a single pulse of light energy, you can also focus the light energy in a very small amount of time as well. And that's exactly what this machine does. Now, a single nanojoule is a very, very small amount of energy. In fact, if I get this apple, it's 1 billion times smaller than the energy it takes to lift this apple just 1 meter up in the air. So it's a tiny amount of energy, but what happens next is going to change all that. So we're going to watch a shot unfold on the National Ignition Facility now. So what happens is the laser beam gets generated, and it's just tiny. In fact, it's just 20 nanoseconds long. But because the speed of light is fixed, this creates a pulse of laser light that's about 6 meters long. And the first thing that happens is the fledgling laser beam gets split into 2 sets of 24 smaller beams, and then heads to some laser amplifiers that boost the energy 10 billion times. And this is just the start. Next, the laser light gets split again into 192 different beams, and it then goes through several extra rounds of amplification. And what happens is there's a special type of glass called laser glass, and flash lamps fire, and they dump hundreds of millions of joules of energy into the laser glass where these beams can pick it up. And all told, the boost in energy that these laser beams get is 4 million billion times over from that starting tiny amount. Now, what's happening is the beams are going back and forth and they're getting amplified, and eventually they're going to have their last amplification and they're going to head towards a target chamber. And on the way to the target chamber, they're going to pass through some crystals, and those crystals are going to change this red infrared light to ultraviolet light. Again, a light we can't see, but it's packed with high energy packets of light called photons. And as the beams approach the target chamber, they're going to go in mirrored paths all around it and head towards a tiny little gold box, a tiny little gold cylinder, where they are going to enter the sides and heat up the insides of the gold. And that gold is going to absorb the ultraviolet light and re-emit it as X-rays. And by the way, this tiny target is only a few millimeters long, and it's cooled to 19 degrees above absolute zero, which is colder than the surface of Neptune. So these are really crazy conditions. When those X-rays are generated, they go towards a tiny capsule of fuel about the size of the pupil in your eye, right at the center of the gold box. And when they hit the outside layer, I think we're about to get the conversion to ultraviolet light here. Here it goes. When they hit that outside layer of fuel, they create a rocket effect. They ablate off the outside of the fuel capsule and cause the rest of the capsule to start to collapse at 350 kilometers per second. And right at the center of this capsule of fusion fuel, the pressure reaches 300 billion times Earth, temperatures of tens of millions of degrees, conditions similar to in stars, atoms ripped apart, smashing into each other and doing nuclear fusion reactions, around 1 billion of them. For a brief moment in this experiment, a tiny star has been lit and energy from fusion reactions released. Now, we're going to come back to this amazing experiment later, but first, I want to talk about what just happened. That is, what is a nuclear fusion reaction? Well, first of all, it's not like the chemical reactions you're used to when you say, set off a wood fire or burn coal or anything like that, or, wine turning into vinegar with oxidation. It's a nuclear reaction, and that means it changes the nucleus of atoms. And if you don't remember what's inside an atom, this is a helium atom, and right in the center, really, really small, is a nucleus with some positively charged particles. In this case, 2 protons, positively charged, and 2 neutral particles, neutrons, and then the electrons are all around the outside. And nuclear fusion and nuclear reactions in general change what's in that nucleus, and that's why they're called nuclear. And actually, fusion is not the only nuclear reaction around. It has a much more famous cousin, nuclear fission. So fission is the reaction that powers the nuclear plants you hear about today. It takes very large atoms, very large unstable atoms like uranium, and it gives them a bit of a kick from a neutron, so they split and fall apart, releasing huge amounts of energies huge quantities of energy in the process. Now, nuclear fusion is different. It takes smaller atoms, lighter atoms, and combines them to make larger atoms, plus, in some cases, a huge amount of energy too. And fusion is a really important reaction for the universe because it kind of turns the universe into this Lego set where if I take enough small atoms, I can build up bigger and bigger atoms. And of course, we're all made out of atoms. So fusion is kind of behind all of the stuff that we're constructed out of. Well, let's meet the specific fusion reaction that star builders are trying to do on Earth. So these are the two special types of hydrogen that star builders are trying to use in earthbound experiments. So we've got deuterium and tritium. So deuterium is about twice as massive as ordinary hydrogen because of its extra neutron. And it's actually really common on Earth. In fact, in every briny bathtub of seawater, there's about 5 grams of deuterium. The second ingredient that star builders want to use to do fusion on Earth is a type of hydrogen called tritium, which is about 3 times as massive as ordinary hydrogen. Now, the thing with tritium is it doesn't actually exist on Earth, certainly not in any large quantities, because it decays over time. So instead, what star builders do is get some lithium and strafe it with neutrons to turn it into tritium. And lithium is widely available on Earth. So the star builder's recipe is really to take these two, combine them in a nuclear fusion reaction to produce energy. And what comes out is a neutron, a neutral particle, and a nucleus of helium. Now, the amazing thing about nuclear fusion, compared to perhaps the other reactions that you know about, is you don't need to do very much of it to generate a whole load of energy. So if I was to take just a single milligram of the fuel for fusion, the kind of fusion that star builders are trying to do, it releases the same energy as burning 19 kilograms of wood, 10 kilograms of coal, or 7 kilograms of crude oil. So that's a difference, an energy difference, mass for mass, of 10 million between coal and fusion fuel. And in fact, fusion even releases more energy kilogram for kilogram than nuclear fission does by about a factor of 4. So it's actually the most energetic reaction that we can lay our hands on Earth with the materials available here. Now, fusion isn't just something that star builders are trying to do that doesn't happen anywhere else. It's actually really prevalent in the universe. So fusion happens all the time in the heavens. They're what make the sky at night breathtaking. All of those stars are actually mini fusion reactors. Well, actually, not many at all, very big fusion reactors, much bigger than anything anyone's doing on Earth, thankfully. And of course, our own sun is no different. It's a star like any other. Fusion is a reaction that makes the sun shine. And although the reaction that the sun is doing in fusion is not the same as the one star builders are trying to do on Earth, it is still using up hydrogen in fusion reactions. In fact, every single second, 600 billion kilograms of hydrogen react, yielding 4 billion kilograms worth of pure energy. I think that's absolutely extraordinary. Kind of puts attempts to do fusion on Earth into perspective. But it's not just stars where fusion is happening in the universe. It actually happens not just when stars are alive, but also when they die, and in dramatic fashion. So what I've got on the left-hand side here is a false color image of the remnants of a supernova. And a supernova is when a star explodes. It's kind of the dying gasp of a star. And they're really dramatic events in our universe. They can outshine entire galaxies. Now, the energy of a supernova isn't actually provided by nuclear fusion, but they do trigger lots of nuclear fusion reactions. And actually, that's our main source of some of the larger elements. And it's not just fusion that's happening in space. If we turn the clock back as well to the beginning of time, fusion was there too. In the first 1,000 seconds after the Big Bang, fusion created elements like helium, lithium, and beryllium. And as I said, most of the elements we're made out of are actually created by fusion, either in stars, in the Big Bang, or in supernova. So fusion happens all the time in the universe and has done since the dawn of time. But why are star builders so interested in reproducing it on Earth? So star builders are interested in fusion on Earth because right now, today, we're in an energy crisis. And fusion promises to be a new and clean energy source that we can add to the energy sources we already have available. Now, you might say, why do we need more energy? Or, what's important about energy? Well, energy makes life good in all kinds of ways. Right now, you wouldn't be able to listen to me if you didn't have electricity powering your computer or your phone to join this call. And, it's definitely true that some countries could cut back on the amount of energy each individual person uses. But there are many other countries where more energy would improve people's quality of life substantially, or where the population is growing and, those new people who are coming into the world and doing exciting things in art and science are going to need energy for their lives too. So we're going to probably need more energy in the future for the planet. But to get a better picture of the problem and why I call it an energy crisis, let's look at how we're powering the planet today. So this is the energy consumption of the entire planet. And let me talk you through what's going on here. So first of all, on the bottom there, on the x-axis, we've got the year up to almost the present day. And at the y-axis there, so going upwards, we've got world energy consumption in something called exajoules. Now, I mentioned nanojoules before, and they're really small, but exajoules are mind-blowingly big. So an exajoule is a million joules. So it's an absolutely phenomenal number. And actually, the USA uses about 95 exajoules a year. The whole world, about 620. So what I've done is I've broken down the world's consumption of energy into the different energy sources here. So right at the bottom there, you can see oil, and then coal, and then gas. And those are all fossil fuels. And the next one that you can see there is biomass, and that includes things like burning wood. And then above that, you can make out there's a sliver, which is due to hydroelectricity. And fusion's cousin, nuclear fission, appears too. That's in the sliver above that. Now, in the present day, renewables are only responsible for a tiny sliver of our total energy consumption, which you can just see at the top there. And actually, the majority of our energy today, 80%, even though we talk about things like climate change all the time, 80% of our energy is still coming from fossil fuels. And this is a big problem. First, fossil fuels create air pollution, and that's estimated to kill around 7 million people a year. But second, burning fossil fuels produces carbon dioxide and other greenhouse gases. And well, let's see, I'm going to show you a chart now. And I want you to see if you can guess where we started burning fossil fuels on this chart. Yeah. So the world went through an industrial revolution and we started burning fossil fuels, and that brought many benefits to the world. You know, we're healthier and wealthier in ways that would have been really hard to imagine in, say, 1600. People from that time wouldn't even recognize life today. But our burning of fossil fuels has done extraordinary things to Earth's climate, and the concentration of carbon dioxide has zoomed upwards. And the carbon dioxide we've released has had a pernicious effect on the planet. It's one of the main consequences is that it has warmed it considerably. So this chart shows how temperatures on planet Earth have changed over time as a distribution. And what it's essentially saying is that the average day to day is much hotter than it was in, say, 1900. And in fact, the average warming since that time is about 1.2 degrees Celsius. Now, that might not sound like much, but even small increases in average global temperature are synonymous with quite dramatic changes. So already today, with the effects of climate change we have, it's estimated to be contributing to the deaths of 150,000 people per year. And if we go much further, if, for example, we breach 2 degrees, we would expect to see life-threatening heat waves become even more common, coral reefs to be completely wiped out, crop failures, flooding, lots of bad things that we don't really want to happen. And in fact, really recently, we've had a taste of some of those things just this summer, the Californian wildfires, the flooding in Germany. Both of those, scientists think, would have been much less likely to happen were it not for human-caused climate change. So because of the harms, and because of the harms burning fossil fuels will continue to do unless we control it, we really need to throw the kitchen sink at climate change. You know, and that means renewables, absolutely. It means nuclear fission like we have today. And it's striking that the countries that have really managed to get off fossil fuels are using a lot of fission. And it means trying out things that as yet haven't been demonstrated at scale, but might be able to contribute to a clean energy portfolio. And the star builders really believe that nuclear fusion could be one of those energy sources. Why they're so excited about fusion, and why you might have heard fusion talked about as the holy grail of energy, is that fusion reactions don't produce carbon dioxide or other greenhouse gases. They create small amounts of helium, really small amounts, but that's an element that's expensive and actually in short supply. But another reason is that the fuel for fusion could last us a really long time. at least 2,000 years, which is a lot longer than fossil fuels, but potentially as long as 30 million years, if we can recover the raw ingredients for the most popular type of fusion reaction from seawater. Now, importantly as well, because you say the word nuclear, it can make some people worried. For me, nuclear is a tool like any other. It has good points and it has bad points. And if you use it carefully, you can take advantage of those good points. But some people are legitimately concerned about nuclear fusion and some of the risks that it can have. But unlike nuclear fission, fusion reactors can't melt down and they don't produce that really long-lived radioactive waste. They do produce some radioactive waste of the target chamber or the chamber because it gets irradiated by neutrons over time in operation. But how long that radioactivity lasts is much, much shorter than the kind of radioactive waste that's produced from fission. Now, I think our biggest problem right now is climate change. So I think fission's great, but fusion promises to be really good on that dimension too. And in fact, fusion, one of the reasons why star builders are so excited about fusion is that it's a real complement to our other likely major source of power, which is renewables. Renewables are absolutely fantastic. They're never going to run out. They also work today, which, the star builders would be first to admit fusion isn't ready to plug into the grid just yet. They're also really cheap. So solar and wind are actually the cheapest forms of power now, and that's unlikely to change. But like any energy source, renewables do have some downsides. They can be a bit unpredictable, and maybe we'll invent advanced forms of batteries that can help with that. But another downside is that they do need to be in the right place. And because the energy that they tap into is very diffuse, you do need large amounts of area to power even a modest number of homes. So, for example, to power the UK solely using onshore wind turbines would mean covering 17% of the country with wind turbines, which is a huge amount. It would change how the country looks. Solar's a lot better. You would only need 3% for that. All energy sources have pros and cons. And what the star builders say is that for a sustainable energy future, which really gives humanity space to grow, we need a portfolio of energy sources that includes renewables. Yes, absolutely. Probably includes fission too, actually, especially in the short run, and eventually one day fusion. And many of the people I spoke to while I was writing the Star Builders were adamant that fusion power is going to be ready in time to help with reaching net zero carbon emissions, which most countries are aiming to do by 2050 or even 2030. But even the ones who think fusion energy might not be into the grid in time for that say that fusion could still have a big role to play in climate change by providing a big source of energy to extract some of the CO2 we've already emitted. So when I showed you that chart of CO2 rising, that means not just leveling off, but actually reducing it as well. And even after we hit net zero, that's still going to be something that we would want to do. So fusion has a lot of advantages, plus some really cool machines. And that's a big part of why scientists have been drawn to working on it. Now, talking about scientists and being really cool, I think it's time to meet someone who's working in this field. And I'm absolutely delighted that we're joined today by a previous star of the Royal Institution, Dr. Kate Lancaster, lecturer and plasma physicist from the University of York. And Kate, we're delighted to have you here today. And so thank you for coming along. And people don't just want to hear from me for an hour. They want to hear about someone who's actually working on these topics and writing papers and in the nuts and bolts of it. So perhaps you could start by just telling us a little bit about yourself and what you do all day.
Sure. Well, it kind of depends on the day, but so my job is as a lecturer, which is kind of like 3 jobs for the price of 1, essentially, where part of my job is researching in this area of laser-driven fusion. Part of it is imparting my knowledge to the next generation, so undergraduates and postgraduates, and so teaching. And then there's part of it that is what we call citizenship, so it's kind of like I run the Fusion Masters program, for example, but I also spend a lot of time talking to lovely people like you in the audience here about why we are doing this, because frankly, it's very important to engage with everyone on this topic because it's so important for the world and for energy generation. So so that's kind of what I do day to day, really, essentially.
Brilliant. And I think this is a field that's so filled with extremes and kind of exciting things. Do you, because you work in it every day, are you ever kind of like, oh, not fusion again? Or is it more that, it's a job, of course it's a job, but you sometimes stop and think, actually, this is pretty neat?
Yeah, so I mean, I guess you can get bogged down with the minutiae, right? Of day-to-day life. But it's funny, I was down at the Culham laboratory, which is one of the major fusion experiments. It's a magnetically confined, which I'm sure you'll hear about later on in this talk. And they have a summer school, plasma physics summer school. And I was giving my annual lecture on inertial confinement fusion, and I happened to be staying on the Rutherford Appleton site. Now, I worked at the Rutherford Appleton laboratories for 10 years before coming to York on big lasers there doing my research, which I still do. And I started work there 20 years ago, and I was walking around site at dusk as the sun was setting, and I'm honestly still just as excited to be there and to see that stuff now as I was 20 years ago at age 22, as a noob walking on site for the first time. I think if you stop enjoying it, if you start excited by it, then you have to give up, because, science and physics in general, like 9 times out of 10 is failure, right? It's that 1 time out of 10 where it goes right. So something has to keep you there day to day. Otherwise it can get bogged down. And for me, it's the, being in a laser lab, discovering things, but it's also the people that I get to work with, scientists all around the world. I've got friends all around the world. I get to travel all around the world and, just be a very, very small cog in a very big wheel. I know that, right? I'm not important in the grand scheme of things, but just being part of it is very exciting.
I'm sure that's not true, Kate.
That really is.
So maybe you could tell us a little bit about what it's like to work on one of these big lasers. And I know you're at York now and spending less time kind of perhaps on the experiment. But, when I was in fusion, I was doing theory. So I had no idea what you were doing. And I was always very impressed by experimentalists having to know the theory as well, really, and doing the experimental stuff. So I think you always had it a more challenging job. What would a typical day working on one of these big laser experiments look like?
Yeah, so first thing to remember, there isn't a typical day right? in one of these places. So I mean, it's worth saying, maybe winding it back a little bit, in the sense that these facilities are very large scale. Some people do their research in their university laboratories. We are unable to do that, right? So what we have to do 6 months in advance is write a proposal to say, we want to do this sort of experiment. Here's the evidence which said we might get something interesting. Please, sir or lady, give us this experiment. Then you're lucky enough to get given the time, and then you design this experiment, over time for a few months, and then you go down to these big laboratories, and often you're there for 5 weeks at a time, away from your loved ones and all of that entails. And you have to build your experiment from scratch. Sometimes, if you're on a big facility like the ones you're talking about, you don't do that. But my experience is building them up from scratch, like giant Meccano, essentially. So you're spending hours of the day in a darkened laser lab with these putting optics around. So it's essentially what we do with laser experiments. We fire a laser into something, and then you have to surround it with a bunch of instruments, looking at it to peer in to the conditions you've created to try and understand what's going on, to tell you something about the physics. Honestly, that is my happy place. Honestly, if I could die in a place, it would be in a darkened laser lab, because
I'm not sure that would be very good for the laser.
No, but it's just such a, and there's ups and downs, there's stresses and strains over getting this, stuff to work within a constrained time, right? You have to deliver, otherwise what's the point? So there's always that level of stress over it. But just, that first shot of the experiment where you have to go out of the laser lab, it's too dangerous to be in there, you lock up the area, you request the shot, and you hear this alarm go off, and you don't know what it sounds like inside because it's all under vacuum, but you can hear this sort of, and then you look at all the data streaming onto the screens, and you think, have we done it? What have we done? And then you realize, nothing's working. Right, go back in, and it goes over and over. So you're working long days, but one of my major things is making sure people remember to drink and eat, because you can stand on one leg for 4 hours, twiddling a mirror, and forget you haven't had a drink for 4 hours. And I'm largely ruled by my stomach. My top priority is where my next meal is coming from. So I'm sort of like the mother hen to a certain extent, making sure everyone's getting food and stuff as well, because that's very important. So, but yeah, so there's a lot of excitement. There's a lot of frustration. And by the time those 5 weeks are over, you're an empty shell, but it's worth it. It's worth it every single time, and I've done many, many, many experiments now in that period of 20 years. So.
And what about when it goes well? Have you had those moments where, you've really nailed it with a shot on one of these lasers? And you've known straight away?
Yes, it's quite hard to tell at the time. I think you're probably aware of that, is that you will have to go away and do some data analysis. But there've certainly been times where the data sure looks interesting. And I think, you can't really make too many assumptions until you go and look at it. But yeah, they're excited. And honestly, it doesn't happen that much. And actually, quite often, what actually happens is you go away and you scratch your head for a bit with a data set that looked initially unremarkable. And then you go, hang on a minute. And that is really exciting, because you're sitting at your desk kind of scratching your head, and then suddenly it sort of unveils itself. And that's also really exciting. So there are many ways to have that moment, if you know what I mean.
No, I believe it. All right, well, maybe you could tell us a little bit about the research that you've worked on or are working on at the moment, and how it relates to fusion.
Sure. So I would call myself a laser plasma interactions person, right? So firing the world's most powerful lasers into bits of material. How is that relevant to fusion? Well, I mean, you're going to be discussing this amazing experiment at the Lawrence Livermore National Laboratory on a place called the National Ignition Facility, we've just seen the video of, right? They do what's called conventional hotspot ignition. So it's kind of like a diesel engine. They compress the fuel until it kind of self-ignites. Now, it's a lot more complicated than that, as you well know. But the problem is with central hotspot ignition is you can't get high energy gains. In order to make a power station, you need something like 100 times the energy that you put in, which this machine is not capable of doing, or this method anyways. So what I've been working on for basically my whole career is what we call advanced schemes, which you might think, well, you haven't even got this one to work yet. So, but yeah, bear with me. So what I've been working on is what we call a sort of petrol engine version of this, where you compress the fuel and then you ignite it with a spark plug. Now, the reason why you get more energy gain out of that, or why you hope to get more energy gain out of that, is you can assemble more mass to a sort of more moderate density. And if you assemble more mass, you can burn more mass, which means you get a higher energy yield. So our spark plug in this case is a super intense laser. So once you compress the fuel, you fire a super intense laser at it. And when that super intense laser interacts with the fuel, it produces mega amp currents, right? So if you think about lightning is some hundreds of kiloamps. So mega amp currents in the space of, well, something smaller than a ball bearing, right? In fact, probably you're delivering that energy in a space that's smaller than a human hair. And that then, basically that energy that's contained within that current then raises the fuel to, the 150 million degrees that you need for fusion to occur. And then you start getting what we call the fusion burn wave propagating out. And I don't know if you touch on that yet, Arthur, or not, but that's what happens. So I'm interested in the bit where you interact the laser with a solid density, or many times solid density piece of material. How does the laser manifest itself as this mega amp current? And then what happens to that mega amp current? And I've honestly spent all my career thinking about that. It's been difficult up until now, actually, because hopefully this amazing result that has come out of NIF recently, which is that they've got really rather a lot of energy out, may reignite everyone's passion for advanced schemes, because at the moment nobody really cares about that, because we can't even do conventional ICF yet. So hopefully that will make people more excited about what I'm doing, or rather what I'm pretending I wasn't doing. because ultimately what I'm doing is fundamental physics, but actually it will help for advanced schemes in fusion. So that's kind of what I'm doing, essentially.
Fascinating, Kate. Really interesting research area, and one that I think you're right is going to get a lot more interest in the near future.
I hope so.
Well, Kate, thank you so much for answering my questions now. Now, Kate has really kindly agreed to stick around for the Q&A at the end. So if you've got any really difficult questions, just please to save them for Kate.
Thank you, Arthur. Thank you for having me.
Okay, so we've heard from Kate, who's doing amazing work on laser fusion, or related to laser fusion, laser interactions. I want to talk a bit more now about progress to demonstrate fusion, exactly the kind of progress that the work of people like Kate and others is bringing the world closer to. Now, although people have been working on and thinking about fusion since the 1940s, there's been a real step change in the last 5 years or so, and it's an enormously exciting time. So right now, across the world, there are over 100 experimental nuclear fusion reactors planned or under construction. And they're not just public bodies who are building these experimental reactors. We're now seeing an explosion of private sector fusion firms too, which is a bit of a change, actually, from how fusion was done historically. And that's not even the end of the excitement. It's not just that there are more machines and that there's public and that there's private. It's also that people are trying out more different ways of doing fusion than before. We heard about one of the advanced schemes from Kate just then. And because we don't know exactly what's going to work in the long run, it's really a good idea to try out lots of things. That's part of the nature of kind of scientific discovery and research. When you don't know what's going to work best, try out lots of options and see. And as well as all of that, there's a strong feeling that people are really close to demonstrating the first stage of fusion. So before we get too carried away with that, I should say what I really mean by the first stage of fusion and what star builders are actually trying to achieve. Well, let's start out with what it doesn't mean. It doesn't mean just doing some fusion reactions, because the star builders are interested in fusion for energy. So the first thing it means is demonstrating more energy out from an experiment than you put in. This is a pretty fundamental necessity for an energy source. And the problem is that fusion reactions require such extreme conditions similar to those found in stars, that they need a big push in energy to start. So it's a bit like lighting a big fire. You know, you've got some energy in the match and you hold it to the fire. And at the moment, with the experiments that have happened, it's a bit like the flame isn't catching. So scientists are currently trying to demonstrate this proof of principle that you can get more energy out than you put in an experiment. Now, the next kind of phase that you might think about is demonstrating more energy out than you put in to a whole fusion facility. So that's kind of like running the stuff that isn't the experiment, keeping the lights on, keeping the computers on, the instruments, the diagnostics. And that's an important next step. And in fact, in the case of the National Ignition Facility that we saw earlier, that includes charging up the batteries or capacitor banks that dump all of the energy into the laser glass. And then finally, the final stage where people are heading towards is showing that fusion can be a bona fide source of electricity that can power the planet. So right now, the star builders are focused on demonstrating that you can get more energy out from in a fusion experiment. And they have different names for this, sometimes break-even, sometimes ignition. But it's all about demonstrating that for every unit of energy you put in, you get at least 1 unit of energy out, or more than 100%. And as Kate told us, that's not actually good enough for a fusion power plant. You probably need to get at least 30 times as much energy out as you put in, but ideally more like 100 times. But as I said, scientists are currently focused on this first goal. And despite decades of trying, no one has yet reached that immediate goal of 1 times energy out for energy in, not even in a single experiment. And it's not for want of trying. But the machines that people have built have brought us extremely close. So I want to talk a little bit now about how to build a fusion reactor. So how are scientists going about doing this? And this, I think, is where some of the most exciting science and engineering comes in. You've had a peek at some of the machines already, and they seem like something out of science fiction, which might strike you as a bit odd. You know, I said that fusion's ubiquitous in the universe. We see it everywhere we look, basically. So why is it so tricky to do it on Earth? Well, it turns out it is. And if you were going to build a fusion reactor, your first thought might be, well, let's just smash some particles together. And it's not a bad idea, but the problem is that if you're just smashing particles together, you're never going to get net energy gain. It's actually it's not possible to get net energy gain in this method. And the reason for that is that the nuclei that you're smashing together are positively charged. And because they're positively charged and like charges repel, they actually mostly just repel each other. They need to get really, really close for a fusion reaction to happen. So if I imagine that I'm a nucleus of, say, deuterium, and I've got a tritium nucleus coming towards me, what that tritium nucleus sees is kind of a big hill of electromagnetic repulsion pushing it away. And most of the time, if the particles don't have enough energy, what happens is the tritium nucleus gets partway up the hill and then gets repelled and pushed away again. What needs to happen is there needs to be enough energy to overcome that electromagnetic repulsion and get into this deep, attractive valley where another force, the nuclear force, takes over. But the problem is that even with the right energy, this reaction is not very likely. So just firing two particles at each other, the likelihood is very low. What you need is a way of rolling the dice multiple times, again and again and again, so that it doesn't matter if one collision doesn't work, the next one's on the way. So how can we do that? Well, if only we had a working fusion reactor that we could take some inspiration from. Aha! Hello, here's one. It's the sun, our nearest and friendliest fusion reactor. So what makes the sun so good at fusion? Well, I think it has three really important properties. The first is density. So if you've ever been on a crowded tube train or a crowded bus and you've been jolted around, you'll know that you'll have bumped into other people, and it's not very pleasant. But if you're on an empty train or an empty bus, you know that you can get jolted around and you won't bump into other people. Well, density, and the sun is extremely dense, makes lots of collisions happen, as you'll know from your trips on busy transport. But for fusion, this is a really good thing because it means there's lots of collisions going on all the time. And that's one of the reasons why the sun is a good fusion reactor. Another reason why the sun is a great fusion reactor is it's incredibly hot. The core of the sun is at about 15 million degrees Celsius. And what this means is when things are very hot, it means they've got a high average energy. And when they've got a high average energy, that means they're also traveling quite fast. And what that means is that when there are collisions between two particles, or some of the collisions between two particles happen at high energy, and there's enough energy to get over that electromagnetic repulsion and for the particles to come together. And the third reason why the sun is such a great fusion reactor, in some ways at least, is that it confines the fuel for fusion, its fuel, very well. It's got gravity on its side, pulling everything in. And the reason why this is good is because imagine if you had a fusion reactor, but as soon as the first reactions happened, all of the energy escaped. Well, that would stop further fusion reactions happening. Whereas if you can confine that energy, you can help divert that energy to heating up the fuel more and getting more fusion reactions because temperatures help. So confining the plasma is the third ingredient. Now, the sun is obviously on a scale we can't hope to recreate on Earth, and I hope no one wants to. But because it's got such scale and because it's got gravity on its side, it confines energy really well. And in fact, if you could follow individual packets of light called photons, you would find that it takes the average photon hundreds of thousands of years to escape from the sun. So we can't do the sun, but what we can do is recreate some of the conditions of the sun here on Earth. And in fact, like a DJ mixing tracks on a deck, you can take those three ingredients of a good fusion reactor, density, temperature, confinement, and we can mix them up in different ways. So we can't perhaps get as dense as the sun, or perhaps we can't get as well confined as the sun, but we can increase the temperature to compensate. But there's an important part of the sun that I haven't really talked about, which is, and this is, you know, quite a question that I had when I started getting interested in fusion and stars, which is, have you ever thought, what's the sun actually made out of? What are we actually looking at here? What is this stuff? Well, you're going to help me answer because we've got a poll, and I want to see what you think. So A, is going to be fire. B is going to be charged particles. C is going to be plasma, whatever that is. Or D, all of the above. We've got an incredibly smart audience this evening. In some ways, I think all of the above is kind of the right answer in the sense that these are all describing somewhat the same thing. But what we call that state of matter that's in the sun, that has its atoms dissociated into positively charged nuclei and negatively charged electrons, is a plasma. That's what we call it. And it's actually the fourth state of matter, plasmas, after solids, liquids, and gases. And you might not have heard much about plasmas because they have a much worse PR team than the other three states, but they're actually pretty common when you start looking for them. So on Earth, lightning, which Kate mentioned earlier, is a type of plasma. The aurora at the North and South Pole, also known as the Northern and Southern Lights, is a type of plasma. And actually flames are they're not a brilliant plasma, but they are kind of a plasma too. They have some of their atoms being dissociated into charged particles. The glowing stuff inside fluorescent bulbs, that's a plasma, and neon lights are too. And off Earth, plasmas are even more common than on Earth. In fact, 99% of the visible universe is actually plasma, including every star in the night sky. Well, I'm excited that I can show you a real plasma in real time here, but I'm just going to have to do some mood lighting, otherwise you're not going to be able to see anything. So excuse me for one moment. What I've got here is something called a plasma globe. So what this is doing is generating an electric field that tears apart atoms inside this low density gas here. And plasmas are quite strange. And imagine if we had a solid or a liquid or gas in here and I put my hand on this, they wouldn't really care, to be honest, that my hand was there at all. Maybe it would warm up a little bit. It wouldn't be very exciting, that's for sure. But the amazing thing about plasmas is because they have these charged particles flying around and electric fields and magnetic fields, if I touch my hand on here, it will sense that my hand is there and completely change behavior. And plasmas are actually pretty badly behaved. And that's one of the reasons why fusion is so difficult, because as soon as you try and do something with this, it's pushing and pulling on itself and behaving in all kinds of chaotic and unexpected ways. And I'll give you a kind of example of that. And for this, I'm going to turn the lights down even more low. There we go. You can hardly see me now. Whoa, that was lower than intended. And what I've got here is my plasma globe, but also one of those fluorescent bulbs, and it's not lit up or anything. So it's just a normal bulb, no wires here. And what I'm going to do is I'm going to bring it in close to this plasma globe. And you can see there that it's lighting up. And the reason it's doing that is because this is creating an electromagnetic field. And it's just about powerful enough to turn the gas in this fluorescent bulb into a plasma as well and light it up. So there you go, plasmas and electric fields. Now, that's probably enough mood lighting for the evening. So let me just turn the lights back up so that you can see me again. Okay, so plasmas are amazing things, the fourth state of matter, but they're quite badly behaved, as I said. So how can the star builders control them? And it gets worse than just the plasma you saw then, because plasmas for fusion have to be at least 60 million degrees and ideally more like 150 million. So we can't just put them in a glass bulb. In fact, there's no material that can contain them. They just dump all of their energy straight away, losing their temperature, losing confinement. So without a star, scientists have had to resort to other means of trapping plasmas. And there are actually three main ways of doing this. So we've seen gravitational confinement before. Inertial confinement is another approach, and it's something that Kate mentioned earlier. And it's kind of crazy, but the answer to what's confining the plasma in this case is basically nothing. The idea is you just throw it together with the right conditions for the briefest of moments until it shakes itself apart because of a sound wave crossing it. So you just bring it together and let the fusion reactions happen, and it will take the time it takes a sound wave to cross it for it to fall apart. Now that's a brief moment, but a brief moment is a really long time in nuclear fusion. And the chart that I put up here is quite complicated, but the thing to take away is that the timescale here is nanoseconds, so really short. And you can see how long that really short laser pulse is. Well, the power from fusion is even shorter, so the fusion reactions happen really quickly. There's another way of confining plasmas, and it's called magnetic confinement fusion. And because plasmas are made out of these charged particles that feel the electromagnetic force, they respond to magnetic fields. And the way that they respond is they get stuck on magnetic fields. So what you can do is you can create a trap out of magnetic fields and get charged particles stuck on them. And that's another way of confining plasma. So those are the real three ways. And what we're going to see now are some of the machines that are trying to implement these ways to trap plasma and recreate star power on Earth. And the first one I want to show you is the world's most successful Tokamak. And a Tokamak is a particular type of magnetic confinement fusion machine. And this one is called JET, or the Joint European Torus, and it's based at the UK Atomic Energy Authority. Now, JET holds the world record for the total fusion energy released and the record for magnetic fusion power at 67% of net energy gain. So not 100%, but not too far off. Now, that record was set some time ago, back in 1997, and it was only done for a very brief moment, but it was still an impressive feat. And what's exciting is, as Professor Ian Chapman will tell you, they're about to gear up for another round of experiments with deuterium and tritium, and he's hoping that they can smash their record for the total amount of fusion energy generated. So that's a really exciting one to watch. And this thing called the Tokamak, it's a weird device, and it's essentially designed to enable magnetic fields to trap plasma. So it has this shape kind of like a cored apple or a donut. And essentially, it has two magnetic fields that combine to make this kind of helical magnetic field. But the really interesting thing about how Tokamaks work is that actually they have very low density. It's only about 1/1,000,000th of the density of air inside JET. And because they have such low density, they have to make up with it with really high temperatures and quite good confinement too. And they certainly do well on the temperatures. And in fact, the hottest place in the solar system is not in the center of the sun, but it's inside Tokamaks when they're running, for those brief moments when they run. And Tokamaks can reach as high as 150 million degrees, which is astounding. The other thing you need to know about Tokamaks is they're aiming to run continuously as well. So unlike laser fusion, which is a batch process, Tokamaks need to eventually run for hours or even longer. Now, there are different types of Tokamaks around, and this is a private sector firm called Tokamak Energy, which is headed up by Jonathan Carling, and they're looking at a really interesting type of Tokamak design called a spherical Tokamak. And because magnetic fields are used to trap plasmas in fusion machines, the more compact you can make your device, the stronger the overall magnetic field that the plasma fields and the better confinement you get. And one of the really interesting things that Tokamak Energy are doing are using these spherical Tokamaks, which are more compact, to better trap the plasma. And a more compact reactor is probably going to be cheaper to build as well. And that's one of the things that's definitely on Jonathan Carling's mind when he thinks about how to take fusion into a commercial reality. And they're based in Oxfordshire. Now, we've already met the National Ignition Facility, which back in 2018 set what was then the world record for laser fusion or inertial confinement fusion of 3% of net energy gain, which doesn't sound very impressive, but wait. And what Dr. Mark Herman has said, who's the director of that facility, is that by the end of the 2020s, they'll have reached that 100% one way or another. Now, again, inertial fusion is a bit different to magnetic confinement fusion. It obviously doesn't confine the plasma for very long at all, on the order of nanoseconds. So instead, it has to keep the temperature moderately high, not as high as in a Tokamak, but the place where it really wins out is in density. And actually that tiny fuel capsule, even though it's very small, gets compressed by a factor of 30 during an implosion. And what happens is you've got an amount of stuff and then you squeeze it down by a factor of 30. You've then got the same amount of stuff in a tiny, tiny area. And that means the particles are very, very close, which allows lots of fusion reactions to happen. But lasers aren't the only way to trigger fusion. There's other approaches out there. And this was one of the firms and one of the leaders of one of the firms I went to talk to for the book. This is Nick Hawker. He's the CEO and CTO of a company called First Light Fusion. And they're using an electromagnetic railgun to fire a projectile into a target instead of using lasers, but again, for inertial confinement fusion. And as he said, this physics problem of getting more energy out than in an experiment, he believes is going to be solved pretty soon. And the final machine I want to introduce you to is an amazing machine that fell out of favor actually when Tokamaks became a big thing, but have just come roaring back up the charts of everyone's favorite fusion machines. And it's something called a Stellarator. And this is Professor Dr. Sybil Gunter, who's a scientific director of the facility, which hosts this it's quite new, Stellarator called Wendelstein 7X. And it's really amazing because Stellarators were thought to be too difficult to build at one point in the past. But now with modern computing and with superconducting magnets, they're possible. And the magnetic fields on this device are so precise that they're good to 1 part in 100,000. And not only that, but the experimental results they've got so far have already been able to show that they've got confinement almost as good as Tokamak. So I really think Stellarators are one to watch. Now, with all of this activity, you're probably thinking, how close are we to fusion? Are we actually going to do this? And you probably heard the old joke, in fact, it's so old that it's actually been banned by editors at The Economist, that fusion is 30 years away and always has been. So, again, it depends what you mean by fusion. But if we're talking about a gain in energy, a big gain in energy from an experiment, I think it's worth looking at what's happened, not just over the last 30 years, but even further back to 1958, shortly after real efforts to do fusion began, to think about how far fusion has come and how close it is to that goal. So what I've done here is I've created a plot that's going to take us through the history of fusion in time. And what you need to know here is the fusion conditions are on the left-hand side going upwards. So that's the temperature, density, and confinement. And on the bottom, we've got temperature in millions of degrees. And right up in that top corner, that's where the star builders want to get to. So we've got a line for magnetic fusion and a line for inertial fusion. And when experiments get up there, that means they're getting a lot more energy out than they put in. And what we're going to see as this goes forward in time is different experiments, blue for magnetic and red for inertial. And the first experiment on there is one called Zeta, and then you've got the first Tokamak T3. And in the 80s, lots of experiments appeared. We've got Jet appearing with its record there, Nova, one of the inertial fusion devices, Omega, and ultimately NIF as well, which is actually pretty close in terms of the conditions you need for fusion already. So this data goes up to 2019, and we've been in the midst of a pandemic for most of the subsequent time. But even despite that, huge progress has been made on fusion just recently. So one of the big developments is that the world's biggest tokamak is under construction. It's almost complete now, 75% complete in the south of France. It's called ITER, and it is almost certainly on a scale big enough to get net energy gain when it is complete. It's going to have 10 times the plasma volume of the Joint European Torus, which holds the current record for magnetic fusion. So really excited about that coming. Another big thing that's happening in tokamaks at the moment is some experimental results on a tokamak called the Experimental Advanced Superconducting Tokamak based in China. So this picture here just shows 5 seconds of a run. And on most tokamaks, a 5-second run would be quite a good thing because plasmas are so badly behaved that they often tear themselves apart after a few seconds. But in May, East smashed previous records for sustained high temperatures in tokamaks by running at 120 million degrees for 101 seconds, which is really huge progress. And finally, there's been an even more exciting breakthrough in laser fusion recently, and this happened just last month. On the 8th of August, 2021, the National Ignition Facility, the device we saw right at the start, did a shot that smashed its 2018 record 23 times over. And it reached 70% of net energy gain. So 70% of the laser energy put in to the experiment was released as nuclear energy. And the team have actually managed a 1,000-fold improvement in energy release over the last decade. Those improvements coming in big multiples. So it's not 3% to 4%, it's 3% to 70%. it now seems almost inevitable that this experiment is going to be the first to reach net energy gain. So that's going to be an amazing moment in the history of fusion. But it's worth saying that this is still a long way away from producing energy that can be plugged into the grid. This is an experimental facility. It only does 400 shots a year. If it's going to produce energy, something like this would have to run 10 times a second. So let's just imagine for a moment that NIF or another experiment gets net energy gain tomorrow. What next? What do the star builders have to do to finish their journey? Well, there are some big challenges to go. And the first of those is actually just capturing the heat from the reaction and using it to create electricity. Of course, we've done that in lots of power stations before, so I'm sure they'll nail that. The second is that, as I mentioned earlier in the talk, tritium doesn't exist on Earth, and they need to generate tritium to put in the reactor. Now, you can generate it from lithium, like I said, but no one has ever been able to try out generating large amounts of tritium from lithium. The lithium has to go around the reactor in a kind of blanket. And no one's been able to do that because they haven't had a working fusion reactor. But making reactors self-sufficient in tritium is going to be one of the big engineering challenges to come. The other thing is operating continuously in the case of magnetic fusion, or 10 times a second for laser fusion. Some big engineering challenges there, but some big improvements too. Another issue that star builders are going to have to grapple with is that when fusion is really successful, it creates lots of neutrons. And if you choose the wrong materials to build your reactor chamber out of, those neutrons can make the reactor materials brittle. And if you choose the wrong materials, it can make them radioactive over time, more radioactive than in a best case scenario. So they need to do a lot of work on the materials science as well. And finally, and one of the most important in many ways, is they need to make fusion commercially viable. It needs to be cheap enough. If fusion exists, fusion energy exists, but it's 10 times more expensive than the next cheapest power source, that's going to be a problem. Now, some of these challenges can't really be addressed until there are net energy gain experimental reactors. But even so, people are starting to work on them, and advanced facilities trying out some of the physics and engineering behind these are popping up all over the place. Many of the star builders, especially in the private sector, are looking beyond net energy gain towards commercialization. And that makes it a really exciting time for fusion. So there are big challenges, and they could seem daunting. But even so, look how far we've come in what I would definitely describe as, the greatest scientific and technical challenge humanity has ever undertaken. Densities and pressures similar to those found in stars, temperatures even hotter than those found in stars. And, if we should learn anything from the pandemic, it's how even apparently long shot technologies like vaccines based on mRNA can actually pay off big time with enough investment and support. And actually, people joke about fusion being a long way away. It really depends on us and how badly we want this. How far fusion progresses and how quickly is going to depend on how badly society needs and wants it. Now, I want to finish by just saying there's one final reason that I think fusion is worth doing. And it's kind of one last stop on our journey, really. And it's about thinking far into the future. If we as humans ever want to explore the universe beyond our own backyard, we're not going to be doing it on a coal-powered coal-powered rocket. That's not going to work. Coal-powered spaceships. But it turns out that nuclear fusion would be a very effective source of energy for spaceships because it uses only a little fuel for a given amount of energy. So on top of everything else I've said about why fusion might be an interesting thing for us to do as a species, fusion is the only reaction that can take us to the stars. Thank you for listening.